Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to week 4, lecture 2 of dynamic atomic force microscopy methods. The last week we were talking about frequency modulated atomic force microscopy, but more specifically from the point of view of trying to understand the connection between the frequency shifts, which will be one of the observables in dynamic AFM as you approach the sample in frequency modulated AFM, and the total potential energy landscape, which is the sum of the potential energy due to the tip-sample interaction forces and the quadratic well corresponding to the elastic spring of the cantilever. The key things that we came to realize is that, left to itself, the cantilever oscillates in this quadratic potential well. It's isochronous motion, and the frequency is independent of the amplitude. However, when you add this quadratic potential well with the canonical negative, positive kind of potential energy connected with the tip-sample interactions, we find that the total potential energy landscape then depends on Z, the separation. In the sense that when Z starts decreasing, the effect of the interaction potential starts becoming more and more apparent in many ways. One, that the well becomes shallower. Another, that the position of the minimum actually starts shifting. And lastly, that the well becomes it's not going to be quadratic, its shape gets changed. In fact, it often starts becoming asymmetric. As a result of all of these, we came to the conclusion that as one approaches the sample, the potential energy landscape changes in a manner which will typically cause the frequency shift to go negative, or the frequency to become less than the natural frequency, and then increase again due to the interaction forces. We also concluded that the shape of frequency shift versus Z is actually going to depend on the oscillation amplitude you tend to choose. Smaller oscillation amplitudes will tend to capture the negative, will tend to show larger negative frequency shift before turning positive, but larger amplitudes will tend to diminish or cause not so much of a negative frequency shift. In fact, you'll go to positive frequency shifts very fast. So this brings us to now, this gives us a very nice idea of how to relate potential energies to frequency shifts, but we are interested in becoming quantitative here. What we really want to do is to convert the observed frequency shift versus Z into the conservative tip-sample interaction force. So today we're going to talk about the methods that are out there in the literature to actually make this reconstruction. It's a very important theory lecture, and then in the next few classes we're going to focus on, or lectures, we're going to focus on practical aspects of FM-AFM, and then we'll move on to studying literature, where we talk about classic works that use these formulas for quantitative spectroscopy. Now, I would like to take you back to a few lectures ago in week 2, when we derived the fundamental basis of dynamic AFM in terms of the virial and dissipation, and how the virial and dissipation are related to frequency shifts and the excitation force. When we derived all these things, I want to remind you that we had made an assumption in that the motion of the tip was given simply by Z plus sinusoidal oscillation A sine theta about that Z position. When we made that assumption, we were assuming inherently that Z was equal to D star. You remember we've talked about D star as being the equilibrium gap between the tip and the sample, and that Z would be the distance between the tip and the sample, assuming there were no forces. And then if forces are turned on, the tip might actually sag a little bit to another gap D star. So underlying all this theory that we talked about in week 2 was also the fact that assumption that Z and D star were the same, basically this means that you're going to be dealing typically in this situation with stiff cantilevers where the cantilever is going to bend very little due to the tip sample interaction forces, and really you're going to be oscillating the probe and using the frequency shifts to detect what the interaction forces are. So with that assumption in place, you may recall that the frequency shift, which is delta omega naught divided by omega naught, which we're going to represent by the new symbol uppercase omega, is related to the virial as shown by equation 1, where the virial is described by the equation right below that. Now, equation 2 describes the expression for the virial that we've already studied before. It is useful to look at it in a slightly different context and write the virial in terms of this new variable u, lowercase u, which is basically sine of theta. If you make that change of variable, the virial can be written in terms of an integral from -1 to 1, as shown. And when you take this form of the virial and plug it back into equation 1, the expression for frequency shift turns out to be as shown. You can express it either as an integral from -1 to +1, which refer to effectively the extremes of oscillation of the tip, or you can write it as an integral from -a to +a if you want to do the integral with respect to q, which is the actual tip displacement. Now, this formula has been derived using many different methods. The method that we have done in the class is a simple harmonic balance-based methods, but this has been derived using Hamilton-Jacobi formalism, as described in some of these references shown here. It can also be derived using the Krylov, Bove, and Mitropolsky method, these are asymptotic methods for nonlinear oscillators. We're not going to cover all those details because we're going to try and focus on what's the simplest math needed to get to the results, and we feel that using the simple harmonic balance approach that we've been talking about in this class is sufficient to do so. So these results have all been derived before in week 2, effectively. So now the challenge is we are measuring the left-hand side, which is we're measuring frequency shift as a function of z. What we want to figure out is the kernel of the integral, or the integrand inside, which is the tip sample interaction force. This is what is called an inversion process. We have to invert the observables to get the kernel of the integral. And this is not a very easy process, and we're going to discuss first 2 assumptions that are frequently made, and lastly a more unifying approach that is sort of evolving and now has become the more standard way of doing this. Okay, so in the early days of FM-AFM, it was usually assumed that the tip oscillation amplitude is very small compared to the length scale of interaction forces. As we have discussed before, the length scale of interaction forces, especially when you're trying to do short-range chemical forces, is going to be of less than 1 nanometer. So in order for the small oscillation amplitude assumptions to apply, you would need very, very small oscillation amplitudes. So with that caution in mind, let's go and see how one would convert frequency shift versus z into interaction forces when the tip sample oscillation, or when the tip oscillation is extremely small compared to z, the separation between the tip and the sample. Now in week 2 we showed that in this case when a is much less than z, then the virial is simply given by negative kts a squared over 2. Kts is simply the negative gradient of the tip sample interaction force with respect to d. Now we just take this expression for virial and make a substitution in equation 1, and we find that in the case of very small oscillation amplitudes, omega, which is the non-dimensional frequency shift, or the relative frequency shift, is simply given by 1/2 kts divided by k. Kts is simply the negative of the gradient of the interaction force. As a result, since kts is nothing but the derivative of the interaction force, we can invert this in the form of an integral as shown in equation 4, so that the tip sample interaction force is going to be given by 2k times the integral from a gap of interest to infinity of the relative frequency shift with respect to dc, or d psi in this case. Now, Psi in this case is simply a dummy variable of integral, which goes from dLTP to infinity. Let me talk to you a little bit about the dLTP. So this is a notation we've used from some of Giesebel's recent work. LTP refers to the lowest turnaround point. What it refers to is the fact that as the tip oscillates, Z is the average gap between the tip and the sample, and as it oscillates, Z minus A is going to be the closest approach distance, or the gap at which it turns around, the tip starts turning around. So dLTP refers to the lowest point in this oscillation cycle. Now, in the context of extremely small oscillation amplitudes that we have considered here, we're already assuming that the oscillation amplitude is much smaller compared to Z. As a result, there really is no difference between dLTP and Z in the case of extremely small oscillation amplitudes. However, we will still stick to dLTP for the limits of the integration because it makes it consistent with the other formulas that we're going to be discussing in a bit. All right. So equation 4 would be used if you had omega as a function of Z. You would simply take an experimental curve as shown on the bottom right, which would be relative frequency shift as a function of Z. If you want to know the tip sample interaction force, the conservative tip sample interaction force at a certain gap dLTP, all you would do is to take an integral of this relative frequency shift with respect to Z in the shaded area that I've shown, multiplied by 2K. K is the effective spring constant of the oscillator. And that would give you the value of the interaction force at that gap. So it's a very elegant interpretation and very easy to understand. However, it requires the oscillation amplitudes to be extremely small compared to the interaction length scale of the forces, tip sample forces. And so this formula would obviously not be valid for short-range interaction forces, but for long-range interaction forces like long-range electrostatic forces, it might still be used. So the community, after they recognized the shortcomings of this inversion procedure, realized that one needs to go towards the opposite case, that more likely when you're trying to do short-range chemical forces, that your oscillation amplitude is going to be large compared to the decay length of the interaction forces that you're trying to sense. So in this particular case, the large amplitude assumption came out. This is when A is much greater than Z. The derivation that I'm going to talk to you about in this case is basically derived from work by Giesebel and Bielefeld in this article that's mentioned out here. But what's key to understanding the large amplitude approximation are two important things. First of all, it helps to rescale our relative frequency shift and convert it into a quantity called gamma that I've defined, which is simply the spring constant times a to the 3/2 times the relative frequency shift. And when you do that, you can rewrite gamma in terms of equation 6. It's a simple rearrangement of equation 5. And when you reorganize this, the key point in the assumption is that the second term in the integrand, which is shown in blue, if one thinks about it, it's an interesting quantity in that Q basically is the tip displacement. It's going to vary from, as the tip is here, Q is going to go from 0 to plus A, back to 0 to minus A, back to 0, right? And the interaction forces are going to be encountered at the very bottom of the swing. At the very bottom of the swing, Q is going to be equal to, effectively, negative A. So if you set Q equal to negative A in the second term in the integrand here, Q equal to negative A, the second term in the integrand is basically 1. So the idea basically being that the tip sample interaction forces shown in the first term are going to be non-zero only when the second term is approximately 1. So we can safely, in this approximation, get rid of the second term, stating that the second term is effectively 1 or approximately 1 when the tip sample interaction forces are active. So this is an important implication of this assumption. The second implication is the integral, you notice, goes from negative Q equal to negative A to positive A. Now, when you're doing in the large oscillation limit, the interaction forces are being felt pretty much just at the bottom of the swing. So as the tip moves away from the sample, the integral that we have to plus a, it needn't be plus a, it can be an integral all the way to infinity, regardless of the z position you're at. The reason, again, is the assumption in the large amplitude case is that regardless of what z you're at, the oscillation amplitude is so large that when the tip is at its furthest turnaround point, that the interaction forces are going to be zero. So with those two implications in mind, one can invert this relationship and arrive at an expression for the tip sample interaction force at the lower turnaround point, which is the DLTP, is given by this integral expression. So what's important here is that one needs to recognize that in an experiment, what one would do in this case is to plot the relative frequency shift omega versus z, and then one needs to take a derivative of it, d omega dz, and then take an integral and weight it by this particular function that's the first term in the integral. And it has to be done numerically, basically. And then one can back out the tip sample interaction force at DLTP. Now, the problem with this approach, of course, is that, in general, how do you know which amplitude is large, which amplitude is small? One doesn't really know. It depends. You need to know a lot about your sample and your tip sample interaction forces to know for sure whether one formula is applicable and the other formula is not. In fact, one of the challenges is when you're doing an approach curve on the sample, you could have situations where to begin with, the oscillation amplitude is large compared to z, but as you come much closer, the oscillation amplitude becomes comparable or becomes small compared to the interaction force range. So from the early days in FM-AFM, there was this need to come up with a way to invert this frequency shift regardless of the oscillation amplitude, or without assuming small or large oscillation amplitude. There are two approaches today for getting over this problem. The first was developed by Sater and Jarvis in a very well-known article, which is referred to here. But what they basically do, and you can look at the appendix for more details, is they come up with a formula that relates the conservative part of the tip sample interaction force at the DLTP, which is the tip sample gap at the lower turnaround point, in terms of this integral. This 2k multiplies the whole integral. The integral contains of three terms. The first term is just omega, then there's a second term and third term. Just by looking at this, you'll recognize that the first term in the integrand is basically the formula from the small amplitude assumption. The last term is simply the formula from the large amplitude assumption. And the middle term is basically the new term that is added in this formula. But how this was done was basically the whole process was actually done in Fourier space, and there was a Padet approximation made, and using methods of fractional calculus, really what's been done very cleverly in this formula is there's been a very elegant interpolation between the large amplitude and the small amplitude limits, which actually performs very well in practice. Now, having shown this formula that allows us to convert frequency shifts into tip sample interaction forces for arbitrary amplitudes, it's important to keep in mind that when you go ahead and try to implement this on your own experiments, there's going to be some challenges. The first is that in practice, omega is not a continuous function of z. It's actually taken at discrete points. And those discrete points need not be equally spaced apart necessarily. That's one thing. And the second thing is that if you look at the second and third terms in the integral, they actually can become singular whenever psi approaches DLTP. So when you're implementing the conversion process, you have to use a discrete form of these integrals, which properly need to account for the singularities. And the reference is shown here where you can look up the process of actually doing so properly. But when properly taken into account, you can get pretty reasonable results out of this method. there's been another method which is also called the matrix method, which is pioneered by Gazebo, which again uses the basic relationship that we derived in the previous slides, but instead of trying to do a smooth fit between these two cases, it literally takes the quantities as described in the last slide and evaluates them at many different values of z. And at the end of the day, what you have to do is to invert a very large matrix to actually get the interaction forces. Again, the details are given in this particular reference. There are advantages and disadvantages to each method, but currently in practice, these are the two main approaches that are out there in frequency modulated AFM to convert frequency shifts into tip sample interaction forces. Here's one example. This is taken from the work of Oscar Kustans and Morita's group in Japan. On the left is shown at room temperature frequency shift as a function of z. And what you see in the gray shaded part is actually many different frequency shift versus z curves superposed on top of each other, and the black curve through them is the average value. So this shows that this is a very well controlled experiment, that you're able to get exactly the same frequency shift as a function of z, and the tip is not, the atoms on the tip or the atomic structure of the tip is not really changing during the repeat experiment. So this is a very carefully controlled experiment that shows very repeatable results. When you take the average value of frequency shift versus z and apply the Sater-Jarvis formula that I discussed in the last page, you can reconstruct in red on the right the tip sample interaction force as a function of dLTP as shown here. And you can see that the data were required for when the frequency shift was negative, but just starting to turn back up, which is why when you look at the interaction force, you actually see the interaction force is starting to turn back up as well. So there are very important conclusions in the frequency modulation, in the force spectroscopy community of looking at the trends of these interaction forces, because they tell you a lot of information, especially about chemical forces, short-range forces, which is of a lot of interest in surface science. So with that, I'd like to conclude, and we'll continue our discussion about some practical experimental issues in FM-AFM in the next class.